The next speaker for this session is Cristina Maria Pacurar from Transylvania University in Brașov. Please, Cristina.
Good evening. I will try to share my screen. I'm not sure how to share my screen.
E o săgeată acolo în dreapta sus lângă Liv.
Cred că am găsit-o. Da, am găsit.
Hello,
Mulțumesc.
profesor Petrușel. Hello. Faceți full screen și apoi e bine. Ok.
My name is Cristina Maria Pacurar and I'm a PhD student at Transylvania University of Brașov. And my presentation today is entitled The Countable Fractal Interpolation Scheme Involving Rakotch Contractions. After the presentation is an introduction, then we'll move on to the main results and in the end some particular cases. Fractal interpolation is a special method for constructing a continuous function which passes through all of the points of a given system of points. Consider the given set of data, x, y, y, I, where x, I are sorted in an ascending order, and they are part of the closed interval, which we'll note with capital I, and which is the closed interval x0, xn. Then the fractal interpolation function is a function defined on capital I and with real values, which interpolates the given data, such that its graph is the attractor of an iterated function system. The notion of iterated function systems is a notion which was introduced by Hodgkinson. Fractal interpolation functions were introduced by Barnsley, and they have been intensively studied ever since. The main difference between fractal interpolation and other types of interpolation techniques is that the result of the interpolation, meaning the continuous function, is not necessarily differentiable at any point, thus being more closer to natural world phenomena and providing a more powerful tool in fitting real-world data. Among the directions of research related to fractal interpolation functions, we mentioned the one by Barnsley related to hidden variable fractal interpolation. There have also been extensions to higher dimensional cases, and another more recent direction of research is due to Rie, and he proposed the replacement of the fixed point result, which guarantees the exaction of the fixed point of the fractal interpolation function. And he replaced the Banach contractions with Rakotch contractions and obtained new results. Another direction of research is related to countable fractal interpolation, which is based on countable iterated function system. Countable iterated function system is a notion which was introduced by Secelean, and also Secelean proved that there exists a fractal interpolation function which corresponds to the countable system of data delta if the sequence xn is strictly increasing and bounded, and the sequence yn is a convergent sequence. Combining the last two lines of research, the one initiated by Secelean and the one initiated by Rie, we propose a new fractal interpolation scheme for countable systems of data and countable iterated function systems which are composed of Rakotch contractions. I'm sure everyone knows what a Picard operator is, but even so, given a metric space X with the metric D, an operator F is called a Picard operator if F has a unique fixed point, we'll note it with F star, and the limit of F composed n times with itself as n approaches infinity for every X is the fixed point X star. For a function phi defined on 0, infinity, and with values in the same interval, and the metric space X with the metric D, a map F is called a phi contraction if the following inequality holds. A map is called the Matkowski contraction if it is a phi contraction where the function phi is such that it is non-decreasing and the limit of its iterates as n approaches infinity is 0 for every t greater than 0. A metric given a metric space X with a metric D, a map F is called a Rakotch contraction if it is a phi contraction where the function phi is such that the function alpha given by phi of t over t for every t greater than 0 is non-increasing and is less than 1 for every t greater than 0. As a remark, each Banach contraction is a Rakotch contraction, and each Rakotch contraction is a Matkovsky contraction. The next result, fixed point result, is due to Matkovsky, and it states that given a complete metric space X with a metric D, if the map F is a Matkovsky contraction, then F has a unique fixed point, which we'll note with X star, and the limit of the iterates of F is that fixed point, which actually means that F is a Picard operator. Considering a metric space, a compact metric space X with a metric D, and the sequence of continuous functions Fn, the countable sequence of continuous function, we call a countable iterative function system the pair formed with the metric space X with the metric D and the countable sequence of continuous functions Fn. The fractal operator associated with this countable iterative function system is the function Fs, which is defined on the set of all non-empty compact subset of X and with values on the same set, and it is defined as the closure of the reunion of all the constitutive functions Fn applied on the compact K. If the fractal operator is Picard, then we say that the countable iterative function system S has a attractor, and the fixed point of the fractal operator is called the attractor of the countable iterative function system S. We will note this attractor with a sub S. Sechelin proved the following result, that if the constitutive functions Fn of the countable iterative function system S are Matkovsky contractions, then the fractal operator Fs is a Matkovsky contraction, and as we saw, if it has a fixed point, then it has then the countable iterative function system has a attractor. Considering Y with metric D a compact metric space and the countable system of data, which we'll note with delta, the system in 1, if the sequence xn is strictly increasing and bounded and the sequence yn is convergent, then the system of points defined in 1, the system delta, is called the countable system of data. We will set the following notations. We will note with A, x0, with m, y0, with B, the limit of the sequence xn, and with capital M, the limit of the sequence yn as n approaches infinity. An interpolation function corresponding to the countable system of data delta is a continuous function which is defined on AB and which has values on y, such that f of xn equals yn for every n greater or equal to 0. We will now construct a family of functions, of continuous functions, which will be the constitutive functions of a countable iterative function system whose attractor is the graph of the interpolation function interpolation function corresponding to the system of data delta. And to do so, we will first construct a family of homeomorphisms Ln defined on AB and with values in xn minus 1 xn, such that there exists an Ln in 0, 1, such that the following inequality holds. And moreover, we need that Ln of A equals xn minus 1 and Ln of B equals xn, and the supremum of Ln is less than 1. Also construct another family of continuous functions, Wn, defined on the product of a, b, and y, and with values in y. And we define those functions such that Wn of a and m equals xn minus yn minus 1, and Wn of b and capital M equals xn equals yn, for every n greater than 0. You also need that the limit as n approaches infinity of the diameter of the image of the functions Wn to be 0. Now we can construct the family of functions Fn such that x goes into Ln of x and y goes into Wn of x and y. Considering C of AB, the set of all functions which are continuous and are defined on AB and with values on y, and such that f of A equals m and f of B equals capital M, this space endowed with the uniform metric forms a complete metric space. Now we can construct a function tf given in the following way based on the functions wn and the family of functions ln, and we can see that t of f, the function t of f, is well defined, and t of f is in C of AB. And having this remark, we can now define an operator t on C of AB and with values on C of AB, and we'll define the operator t of f to be the function tf for every f in C of AB. Based on the following remark, the operator is well defined. State the main result. Considering a countable system of data delta, if the functions wn are Matkowski contractions with respect to the second argument, which means that there exists a non-decreasing function phi such that the limit of the limit of phi composed with itself n times is 0 for all t greater than 0, and the inequality star holds for every x in AB and every y and y prime in y, then T is a Matkowski contraction. Since the time is short, I will the proofs. Now move to the second result, which states that for a countable system of data, if wn are such that they are Lipschitz in the first argument and the Rakotch contractions in the second variable, which means that there exists an L greater than 0 and a non-decreasing function phi, which satisfies phi of t over t is less than 1 for all t greater than 0, and phi of t over t is non-increasing, such that the following inequality holds, then the functions fn are Rakotch contractions with respect to the metric d theta, described as follows, where theta is in 0, 1, and it has the following expression. I'll also skip here the proof, and I'll go to a remark. We can observe that if delta is a countable system of data, if the functions fn are Rakotch contractions with respect to the metric d theta, and we'll prove that they can be as such in a particular way if we choose wn in a particular way, then the countable iterated function system composed of the metric space AB in times y with the metric d theta and with constitutive functions fn has a tractor, which means that there exists a unique A sub s, which is a compact subset of the space, such that the fractal operator of this A sub s is A sub s, and the attractor of the A sub s is a fixed point of the fractal operator. Now, considering delta a countable system of data, such that wn satisfy the hypothesis from the previous theorem, which were that wn need to be Lipschitz in the first argument and Rakotch contractions in the second argument, then there exists an interpolation function f star corresponding to the countable system of data delta, such that the graph of f star is the attractor of the countable iterated function system S composed of the metric system AB times y with the metric d theta and the constitutive functions fn. And the last theorem, under the framework of the previous theorem, we've also proved that the limit as n approaches infinity of t composed with itself n times for every f0 in C of AB is actually the interpolation function f star. In particular cases, we can the family of homeomorphisms Ln in the following particular way, for every x in the closed interval AB. And for y being a compact real interval, we can choose wn in two ways. In the first case, we can choose wn with cn, gn having the following expressions, and dn being in 0, 1 such that the limit of dn is 0. And in this case, we can prove that wn are Lipschitz in the first argument, and they are contractions, Banach contractions in the second argument. And if they are Banach contractions, then they are Rakotch contractions with the comparison function phi given by phi of t equals c times t for every t greater or equal to 0. In the second case, we can choose wn with cn defined as such, and Gn having the following expression. And in this case, we can prove that Wn are Lipschitz in the first argument, and they are Rakotch contractions in the second argument, but the comparison function is phi of t, which is t over 1 plus t. And although it is a Rakotch contraction, is not a Banach contraction, which proves that our results are more general than the previous results. In the two cases, we can choose the family of functions Fn, which are the constitutive functions of the countable iterated function system, in the two following ways. In the first case, we will choose Fn as such, and in the second, Fn has the following expression. Thank you for your attention.
Thank you. Thank you very much for the nice presentation. I would like to ask, we can afford a few questions or remarks, if any. Please.
May I?
Yes, please, Professor Petrushel.
So very interesting talk and a nice topic for your PhD thesis. My question is related to the notion of Rakotch and Matkowski contraction. You mentioned that any Rakotch contraction is a Matkowski contraction. And my question is, if you know there is any example of Matkowski contraction which is not a Rakotch contraction?
I cannot think now of an example. I'm sorry. I'm sure I found an example at some point, but I cannot recall it now. I'll have to think about it. I'm sorry.
No, it's not. Because sometimes I have the impression that these classes are very related, so maybe they can coincide. Okay, thank you.
So, thank you for the question. As Professor Petrushel pronounced, my impression is that the exact pronunciation is Rakotch and not Rakotzi, because Rakotch adopted this English spelling for maybe an original Hungarian name, Rakotzi, but it will be pronounced Rakotch, like Professor Petrushel pronounced.
Thank you.
Just not essentially remark. If any other remarks or comments? If not, thank you, Cristina, for the nice presentation. Good luck with the thesis.